Hi everyone. In the past several videos, we've discussed double integrals over rectangles for functions from R2 into R. In this video, we will see how to extend what we have learned about integration over rectangles to evaluate double integrals over general regions in the plane. So since we understand well how to integrate a function over a rectangle, what we would like to do is extend our notion to a general region by just extending our function to be defined on the full rectangle. So if you will sort of imagine, we want to integrate over some bounded region S. So we can imagine we have some bounded subset of the xy plane, which we will call S. And so I have some set S in the plane, and I have some function that's defined on S. So let's imagine I have this function f, and it's going to look like some sort of surface sort of floating up here, and it's going to again be, but it might be sort of bumpy, right? It can do all sorts of things. But I have some sort of surface, lying over here that is what I want to integrate. So this is my function f that I want to integrate over S. So the idea is going to be, well, if I want to integrate this function over this set S, since S is bounded, I can actually draw a rectangle in the plane such that S lies entirely inside that rectangle. Okay. So what I'll do is if I want to integrate the function f over S, I will enclose S in a rectangle Q. And then what I'll do is, okay, I want to integrate f, right? But f isn't defined on all of Q. So I cannot integrate f over Q. So what I'll do is I'll define this function f tilde. We'll think of this as like an extended version of f. And what I'll do is I'll say, well, this function f tilde, I want it to be defined on all of Q. F tilde will be equal to f if I'm actually in the set S. So it'll give me this. If I happen to be outside of the set S, but still in Q, then I'll just define my function to be 0. Okay. Now, if you notice, you think about this from like a volume perspective, right? What I'm doing is I'm integrating over this whole rectangle, but I'm only capturing the volume that's under the surface that's defined on S. Everywhere else, I've set this function to be 0, and therefore I'm not actually picking up any of the value from those outside parts. Okay. So what I want to do is I want to claim that this function f tilde is integrable, and then say that f is integrable. Okay. So sorry, let me actually reverse that. So what I want to do is I want to say f is integrable if this function f tilde is integrable on Q. So we'll say f is integrable on S if and only if this extended function f tilde is integrable on Q. So this function f tilde, right, is defined on all of Q. Q is a rectangle. We already, excuse me, we already know what it means for a function to be integrable on a rectangle. So if f tilde is integrable on Q, then we will say that f is integrable on S, and the value of the double integral of f over S will just be the double integral of f tilde over Q. Okay. Now, practically, this is not how you want to compute anything, but theoretically, this has the advantage of taking integration over a general region and just reducing it to the case of integration over a rectangle. So we can now use almost all of our theory about integration over a rectangle to help us understand integration over a more general region. So most of what we want to spend our time doing in this video then is sort of understanding when is a function f over a general region S going to be integrable, and what properties might I need to make sure S satisfies in order to help ensure that integrability. From there, we'll just look at the logical consequences of all of the integration theorems that we've already built applied to this particular context. All right. So before we get there, I do want to note two sort of important things, or one important thing, and then we'll look at one other one about this definition. So the definition sort of says that this value of the double integral of f over s, it should be sort of independent of whatever rectangle Q I choose to put s inside of, right? So like if s looks like this, right, certainly I could put, here's a rectangle that s lies inside of, but like here's another rectangle, right, that s lies entirely inside of, right? And notice that it doesn't say, the definition doesn't say choose a particular rectangle. It just says for any rectangle, it sort of pretends like you should get the same thing. So this is really a question about whether this is well defined, right? So since I haven't specified a particular rectangle, will I get the same value regardless of which rectangle I use? And the answer, of course, here is yes. And the reason that the answer is yes is because regardless of which rectangle I pick, my extended function f tilde is just going to be defined to be 0 outside of S. So this really is well defined, even though we don't specify a particular rectangle that contains S. So we can actually choose any rectangle that happens to be convenient for us. So then the real question is, we don't need to worry about the rectangle so much. The question becomes for which regions S in the plane and what types of functions F is this extended function f tilde integrable on Q? So just to give you a little preview into sort of how we want to think about this, right? I know that if a function is continuous on the rectangle Q, then it is integrable on Q. However, if I take a function f, which is continuous on S, so imagine I could have some sort of surface here, it's defined on some sort of, some sort of set, maybe there's a set S in the plane. There's my function f. Okay, this is a nice continuous function. However, as soon as I create a rectangle and create the extended function f tilde, even though here we have f, and f is continuous on S, right? My extended function f tilde, in this case, is not continuous on Q, right? So this extended function, right, I'm going to get this, which is continuous, but it's going to have discontinuities along the entire boundary of S, right? So I have to be a little careful here. So that's why this is sort of very specifically phrased for which regions S and which functions F is f tilde integrable on Q, because we need f tilde to be integrable on Q in order for f to be integrable on S. Okay, so we really need to sort of try and make sense of what the problem is here. Now, as I look at this, if f is continuous on S, it's certainly also continuous on, or sorry, let me back up. If f is continuous on S, then f tilde is continuous on S, because f tilde is just equal to f on S. Further, f tilde is continuous on Q delete S, right? It's just constant out here, the function f tilde. The function f tilde is constant on Q delete S, it's just 0. So the function the function f tilde is continuous on the interior of S. It's continuous on the interior of Q delete S. The question is really what happens along the boundary right here, right? Well, we're potentially going to have points of discontinuity, right? Unless your surface just happens to come down and sort of match up nicely, right, with the XY plane there, you're going to have points of discontinuity along the boundary of S. And so the question we have to worry about is that going to cause a problem? Well, think back to the end of the previous video, right? We had that theorem that says as long as your points of discontinuity are a set of content 0, then your function f will still be integrable. So what we may want to do is say, well, can we say something about the conditions under which the boundary of this region will have content 0? It turns out that the answer is yes under nice enough conditions. Certainly the boundary of S will be a set of content zero. And in fact, we're pretty much going to limit ourselves to those particular cases. So let's look briefly. We're not even going to prove this theorem. It's actually one you could prove just straight from the definition of continuity. But um, if our boundary of S is the graph of some continuous function in the plane, okay, or piecewise the graph of some continuous function, then it will have content zero. So if phi is any real valued function that is continuous on a closed interval AB, then the graph of phi, and the graph of phi here again is just defined to be the set of all x points xy such that y is equal to phi of x and x is between a and b, has content zero. So for any region S in the plane, right, if you can think of S as being, say, this, 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 these are three graphs of continuous functions, right? Each of them, this theorem says each of them has content zero, and the union, the finite union of sets of content zero, also has content zero. So essentially, as long as your boundary is continuous, you will be in good shape in terms of knowing that your function, your extended function f tilde, will be integrable as long as f is also integrable. All right. So the first part of the question, essentially, this has to do with, what do we need S? How do we need S to behave? Well, we need S to have at least sort of a continuous boundary. If you start allowing really irregular things, like if you allow boundaries of regions that are like these space filling curves, or like all sorts of bad things could happen. But if we just take the normal graph of a continuous function to be our boundary, then we'll be in good shape. All right. Now, we actually want to further sort of specify the different types of regions we might work with. And we're going to start by looking at sort of some special cases, and then we'll sort of claim and see that, well, we can build other things out of these special cases. So we want to start by defining two different types of regions in the plane. We'll call them type 1 and type 2 regions. And really, again, these are special cases of the boundary is continuous, the boundary is the graph of some continuous function. So we call a region a type 1 region if it is a set of the form S is equal to the set of all xy such that x is between a and b. So on this graph down here, you can see, right, my x values are just ranging from a to b. So on the sides, I'm getting these vertical lines, and then my y values lie between these two functions of x. So my y value ranges from, on the bottom end, phi1 of x, and on the top end, phi2 of x, where I'm going to assume phi1 and phi2 are just two continuous functions on AB with phi1 less than or equal to phi2. So these aren't weirdly overlapping or something. This just gives you a nice region in the plane. One way to think about this is sort of the first, it's sort of one step away from a rectangle, right? A rectangle would have vertical lines on both sides, vertical lines on the top, or horizontal lines on the top and bottom. Here we have vertical lines on the left and right, and then now the top and bottom, instead of being bounded by constants, are bounded by functions. Okay. Now, you might be able to just immediately guess from here, or you probably saw this in Calc 3 also, but you might be able to immediately figure out, right, what a type 2 region is. It's basically sort of, the idea is take this and rotate it 90 degrees. That gives you a type 2 region. But a region of type 2 is simply, now my y values are bounded between two constants. So if you look here, I have these horizontal lines, one at C and one at D, right? And then my x values are bounded between these two functions of y. So I have psi1 of y and psi2 of y. Okay, where again, psi1 and psi2 are some continuous functions. Again, these are like sort of one step away from a rectangle, except now I'm keeping the horizontal sides constant, right? But now I'm letting the left and right sides become sort of functions of y. All right. Now, what we're going to see, we're actually going to prove some theorems related to what happens when we have a type 1 or type 2 region. But before we get there, it's worth thinking about, how do these type 1 and type 2 regions relate to other sorts of regions, right? So imagine, so the first thing to note is you could take, say, some sort of region like this. So here's some region in the plane. And you could ask, is this a type 1 region or a type 2 region, or sort of what's going on here? And in fact, I'm a little worried actually the way I've drawn it. It doesn't, the sides don't need to be wiggly. You could just take a triangle. Okay. Yeah. So if I was to take a triangle like this, the first natural question you could ask is this type 1 or type 2? If we look at this, we could think of this as a type 1 region. So here are constants A and B. My x values are between A and B. And then my y values are bounded between this lower function, which would be like my phi1, and this upper function, which would be like my phi2. Okay. So this is a type 1 region. It also is a type 2 region, right? So if I look at this, I can also think of this. Let me just redraw the triangle over here. So I can also think of this as my y values are bounded between, say, some c and some d. And then my x values are bounded between some lower function psi1 of y and some upper function psi2 of y. So the first is that type 1 and type 2 is not some sort of disjoint classification where things are type 1 or type 2. Okay. Furthermore, it's not the case that every region has to be one or the other. So for example, if you start taking particularly wiggly sorts of regions, okay, this region, let me emphasize this a little more here to make sure I don't. Yeah. This region is neither type 1 nor type 2, right? So the problem here, right, is that if I try to, let's say I tried to make it type 1, so my x values would have to go between this A and this B value. And on the bottom half, I might be, well, no, I wouldn't be okay, because I would come down here and say, I need things to be bounded below here, but this thing that would need to be like my lower bound, this is not a function. This thing that would need to be like phi1 is not a function. Okay, so you could try also twisting this and doing it the other way, but you run into the same problem. The things on the side, you wouldn't have a function anymore. Okay, so it turns out that this region is neither type 1 nor type 2. Now, that might be a little disheartening because you look at this and go, well, the boundary is not that bad. I mean, it's still it's a nice continuous curve, even if it's maybe not a function. And so the good news is that for most reasonable domains that we want to consider, while they may not all be type 1 or type 2, we can always decompose them into some union of type 1 and type 2 regions, right? So for example, here, I could just come and sort of start cutting things. And even if I maybe do this in a suboptimal way, let me just So now that I've done this, let's see. This is now certainly a type 1 region. Okay. Let's see. This over here is a type 2 region. And some of them may be others. I'm just coming up with the first one that I see. I could come and sort of maybe cut here to make my life a little easier. And now it looks like this is a type, it's a type 2 region. Okay. Now this I can sort of split up here to make my life a little easier. Let's see, now this piece up here, I certainly could view as a type 1 region. This piece, let's see, I don't know if I can I do this whole piece now? Yeah, actually, I think I can. Well, I don't know. Let's just make our lives easier. If I just cut all the way across here, now this is certainly a type 2 region, and this thing sitting up here is now a type 1 region. So even though this region, the whole region itself is neither type 1 nor type 2, I can decompose it into a union of regions, each of which is either type 1 or type 2. Okay, so the moral of the story is that while this type 1, type 2 classification is not sort of some complete classification of regions in the plane, it is a useful way. We'll see it's actually helpful in calculating things to think of things as type 1 and type 2 regions. And for any sort of sufficiently nice region in the plane, we can decompose it into type 1 and type 2 regions if needed. All right. So let's see why we really want to talk about these type 1 or type 2 regions. So imagine I have a region of type 1. So again, just to have the picture back in our head, right? The idea is I've got constants a and b, and then these functions b1 and phi2 that are bounding my region. So here's my region. S in the plane is a type 1 region. Okay. Now, if I assume that my function f is defined and bounded on S, and that f is continuous on the interior of this set S, then the double integral of f over S exists, and furthermore, it can be evaluated by iterated one-dimensional integration so that we get that the double integral of f over S is equal to the integral from a to b of the integral from phi1 of x to phi2 of x of f of xy dy dx. Okay. Now, we will walk through a proof of this for type 1 regions in just a minute, but you probably wouldn't be surprised to find we can also come up with a similar result for type 2 regions. So for type 2 regions, right, we get, I mean, it's almost entirely analogous. Just as a reminder, right, type 2 region. So now I have like psi1 constant C, D, and then psi2, right? So for a type 2 region, it looks like this. If I assume that f is defined and bounded on t, and that f is continuous on the interior of t, then the double integral of f over t exists, and the double integral of f over t can be found by this iterated one-dimensional integration, which is the integral from c to d of the integral from psi1 of y to psi2 of y of f of xy dx dy. All right, so what we want to spend the remainder of this video doing is really making sense of and proving this theorem. We're going to do it in the type 1 case because once you understand the type 1 case, the type 2 case is an exact analog of that proof. All right, so let's begin our proof. All right, so remember I'm starting with a function f defined on S, right? And I know that f is continuous on the interior of S. Okay. So I know that on the interior of S, this function f is continuous. And so I want to say, what can I say then about that function f tilde? Okay, well, since f is continuous on the interior of S, the function f tilde, which let's just remind ourselves, f tilde of xy right? It's equal to f of xy if xy is in S, and it's equal to 0 if xy is in Q, delete S. Okay, so since f is continuous here, and certainly 0 is continuous here, then this function is continuous except possibly along the boundary of S. But we're going to assume here that S, right, we're assuming S is a type 1 region. So its boundary are just graphs of continuous functions which have content 0. All right. So what do we have? Now we have this function f tilde, which is continuous except possibly along a set of content 0. That means that f tilde is integrable on Q. So hence f tilde is integrable on Q. Now, okay, I'm on a type 1 region, okay? So I might want to define sort of specifically what rectangle this is. Now, since I'm on a type 1 region, my x values I know are going from A to B. Okay. The y values, now I can choose any rectangle I want, really. I just need to make sure that S is entirely within Q. So what I'm going to do is just going to call this AB to CD, but I'm going to define C and D. C is going to be the minimum for overall X in AB, marker is drying up, of phi1 of X. And D will be the maximum over AB of phi2 of X. So here's the idea. I'm trying to define this rectangle that S lies inside of. I know S looks like this. Well, right, this bottom part is a function. So to define this rectangle, well, I can still just use A and B on the right. Okay, so that's fine. But now here, I'm going to find the lowest point on phi1. I'll make that the bottom of my rectangle. That's my C. Okay. And then I'll find the highest point on phi2, right? I'll make that the upper part of my rectangle. Okay. So I'm just defining this so that I'll have a specific rectangle Q I can work over, and my function lies entirely inside there. Okay. All right, great. So now I have that f tilde is integrable on Q. That means that f is integrable on S, right? That's what we defined for it to mean for f to be integrable on S, okay? So we can sort of conclude this part by saying, so f is integrable on S. F is integrable on S because f tilde is integrable on a rectangle Q containing S. All right. That's the first part of the theorem. The second part is, how do we do the iterated integration piece? Okay. Well, we know that f tilde is integrable, and we have an iterated integration theorem on rectangles. So let's try to apply that here. Okay. So if I look at the double integral over, the double integral over S of f, by definition, this is the double integral over Q of f tilde. And again, we know this exists. That's why this exists. Okay. But now, under certain conditions, right, I should be able to write this as the integral from a to b, integral from c to d of f tilde xy dy dx. Okay. Now, again, what were the conditions I needed for this iterated integration theorem? Well, the first was I needed f tilde to be integrable. I've got that, check. The second piece was that I needed to know something about this, right? I needed to know that this existed for each fixed x. Okay, and it's going to be helpful here to sketch another picture to just help us think about what's happening here. Okay, so I have this set S, and it's on a type 1 region. So when I put a type 1 region down in here, so I've got like, you know, there's B, there's A. I'm going to get these sort of lines here. And then I'm going to have some functions on the sides. And these are going to be, you know, let's see, this will be phi1, this will be phi2. Okay, but now I've sort of gone and I've embedded this inside some rectangle. Now, the way I've defined this rectangle is fairly tight around here. I'm going to make it a little bigger just to help illustrate some points here. Okay, so I have my function f, which is defined above this type 2 region, right? So, you know, it does whatever up here. You know, maybe it's sort of wavy up here. I don't know, right? Could do something like this, you know, whatever it looks like. And maybe this is what it looks like. Okay, above here. And now I have this extended function, which I'll put in sort of orange here. It's 0 everywhere out here, but then up here it takes these values. Now, if I think about fixing a particular x value, so let's say I fix an x value right here, okay? What is f tilde of xy for that fixed x value? Well, I can sort of imagine I just come in here. So on the rectangle until I hit the set S, right, it's just going to be 0. Okay. And then it's going to come up here and it's going to do whatever. It's going to follow along this surface. And then when I get back down here, it's again just going to be 0. So again, you sort of think about taking a plane and just slicing down through this, and you get sort of a line, a constant 0 line segment here, a little function here, and then another constant 0 segment here. Okay. Now, the question is, so for each fixed x, I want to know that this is actually integrable. How do I know that? Well, if I look at this, it's continuous here, it's continuous here, it's continuous here, right? I do have 2 possible points of discontinuity, okay? But we know that for a one-dimensional integral, right, as long as we have a finite number of points of discontinuity, our function will still be Riemann integrable. So I know that this exists for each fixed x because this integrand is continuous except for at most 2 points. Okay, so since this is continuous except for at most 2 points, it is integrable, Riemann integrable, and so this exists. Okay. Now again, when I take a continuous function and I integrate it, I'm going to get a continuous function back except possibly at these 2 points, right? So it will again be integrable. Okay, so again, those conditions were like, I need a of x to exist and I need a of x to be integrable. Those are all satisfied in this case because of how these functions behave when you take slices of them along this rectangle. Okay, so my point here is I can actually apply the iterated integration theorem on a rectangle. And now what I want to do is I want to look at this inside integral. Again, that's sort of finding the area under this green curve here. Well, what I'm going to do is I'm actually going to break this inside integral up, okay, this integral from a to c. I'm going to break this up into an integral from, so imagine I'm starting at, here's c, So I'm going to start with y is equal to c, and I'm going to push it all the way up until I get to this point, which is phi1 of x. Okay, so I'm going to integrate from c up to phi1 of x of f tilde xy dy. Then I'll integrate from phi1 of x up to phi2 of x. So there's like phi1 of x. Then I'll integrate up to like phi2 of x. And then I'll integrate from phi2 to x, phi2 of x all the way up to d. So I'm just decomposing this integral from c to d as an integral from c to phi1 of x, from phi1 of x to phi2 of x, plus an integral from phi2 of x to d of f tilde of xy dy. Okay, and again, all of this is also the integrand of another integral, right, dx. But now if I look at these three integrals, when my when my y values are between c and phi1 of x, my function f tilde is outside, these domain points are outside of the region S, so my function values are all 0. Okay. When I'm between phi1 of x and phi2 of x, now my function values are non-zero because they're f of xy. But once I get to phi2 of x again, and I go between phi2 of x and d, my function values are again 0. So both of these integrals disappear. And so what I'm left with is an integral from a to b of an integral from phi1 of x to phi2 of x of f tilde of xy, but on this interval, f tilde is just equal to f of xy. It's just an integral of f of xy dy dx. And note that that's exactly the formula that we wanted in order to prove this iterated integration theorem. So again, this is very much like the iterated integration theorem for rectangles. It's just that now some of the bounds are no longer constants, right? They are functions of the other variable. Okay. Now, if you want to flip this and do it for a type 2 region, and I would encourage you to try this because it's a good exercise in making sure you understand what everything is doing. You really basically take this proof again and just rotate it 90 degrees. Your x and your y coordinates are going to sort of swap roles in that proof. But it's something I encourage you to try. And if you want to try writing it out and send it to me and have me check it, I'm happy to do that. But this gives you some idea of how this iterated integration theorem comes into being. Now, this theorem is then what is used in the vast majority of like a Calc 3 course to actually compute the values of multiple integrals, right? And in fact, right, it's sort of from a computational standpoint of actually computing these things, right? It can be quite tricky. It can be tricky to identify just from the outset whether something is a type 1 or type 2 region. Once you know whether it's type 1 or type 2 or possibly both, especially if it's both, it can be hard to determine which it's better to think of it as for computational purposes. From the Calc 3 perspective, there's a lot more work to do in order to actually compute these. But the beauty of this is that by simply building the theory on a rectangle, we can very quickly get results about a much more general region. Okay. So we are going to conclude this video here. In the next few videos, what we're going to cover are the major theorems that one sees at the end of a Calc 3 course, namely Green's theorem, Stokes' theorem, and the divergence theorem. These are all theorems which, in certain ways, can be thought of as something like fundamental theorems of calculus for other types of integrals, right? So just as we saw that for line integrals, we had a fundamental theorem of line integrals, we'd like something like a fundamental theorem for multiple integrals, for double integrals. And so those theorems will help us to understand a little better how the values or the integral or double integral of a particular function can be understood through looking at either those values, say, along a boundary curve, or those values related to differential type operators applied to other functions. So again, we'll see connections much like we see in the usual fundamental theorem of calculus. It's just that in this case, there are somewhat more exotic types of differential operators that we'll be looking at to help make those connections.